I also post it in here. Okay. And in Slack.
Also share my screen as usual, and watch stream. And yeah, that's it. I'll briefly check that the recording is, well, the streaming onto YouTube is working correctly. Okay, that works. Yeah. So
Good. Oh, that's a lot of people. Hello, a lot of people. Relatively speaking.
I
Well,
guess people like the theory of deep learning paper, maybe.
like this paper includes both Mech Interp stuff and deep learning theory stuff and tries to connect it.
I don't know.
You started
Skimming
recording?
didn't seem. Yeah, I started recording. We can
Okay.
start.
Like at least how the authors frame it is that like Mech Interp is like biology of deep learning approximately, and deep learning theory is like physics of deep learning or sometimes pure math of deep learning, I would say. So maybe like if you wanna combine these two together, we would need something like chemistry of deep learning.
If
Like maybe when you look
have
at go ahead.
read the thing, you can try explaining it or something.
Yeah, there's I think if you look first at the at the tweet. Oh yeah, I'm gonna post this tweet.
Okay, I guess I can show the tweet first.
Here they, actually it's from the paper. So if you scroll down a bit, there's a table of like what they point at. Oh yeah, that table.
This table.
So like,
Okay.
yeah, I would say Mech Interp is in the universal phenomena. So like here they like show the different things that are studied in deep learning theory and also in Mech Interp, and how there seems to be slight correspondence or slight mapping to physics, that they do similar stuff. So they're arguing actually what we are doing in machine learning seems to resemble physics or deep learning specifically. So like you have these simple solvable settings, I guess in Mech Interp you could say toy models with toy data set and so on. So some of them are like solvable much more easily. So like harmonic oscillator and physics, and you have some simplified limits, like some deep learning theories, like what happens if we make the network in infinite width, for instance?
Yeah.
And
I mean, I feel
that's
like
useful.
that I think that can
Sometimes.
be useful, but often like the simplifications making it kind of make it unrealistic and ignore the interesting things about deep learning or something like that. Like
Yeah,
they can
but
serve you
yeah,
to give you some theoretical limits or some theoretical bounds or whatever, but
yeah.
don't tell you that much about interesting things that happen in practice.
There's a lot of critique for the theory of deep learning that it's like doesn't really have a contact with practice, yeah. But at the same time, there are some results. Like I just learned that there's like they also mention in this paper there's like something called maximal parametric update MIPU. Maybe it's called MUP from tensor programs. Which apparently was used for GPT-4, for example, and it allows you to do zero-shot hyperparameter transfer from small models to big models. So if you do experiments on small models, then you know it will also work on big models, kinda, because the theory is like, if we increase the width, increase the parameters, then the activations are still stable. Therefore, we can increase the model size and we can still transfer the hyperparameters, and it still works using some of the complex math. It's pretty cool that there is some results like that. Yeah. So those are like the simplified limits. There are also the simple empirical laws, like yeah, obviously scaling laws. So you could say that's kind of similar to laws of Kepler, for example. And also like they also mentioned the study of system parameters. Oh, yeah, here's the mu-p. They also straight into this because mu-p, the you are doing hyperparameter transfers by looking at the simplifying limits. So it's in both simplifying limits and in study of parameters. There are step size of sharpness, for instance. Oh yeah. That's apparently also another result that the curvature of like the sharpness of the loss landscape seems to correspond to something like learning rate divided by 2 if you like train a lot, so and the loss landscape gets sharper and sharper. That's apparently also
I'm
some
not sure
theoretical
what
result.
sharpness means in the context of like
uh
very high
I think
dimensions.
they just I think they just define it as the maximum eigenvalues of the second derivative of the loss landscape, something like that, I think. Yeah. So I'm not sure how tractable it. I think the theory was done in a simple setting, so it's much more computer. I'm not sure. Yeah. Uh, I got this from the authors of the paper. Yeah. So and also the universal phenomena. Yeah. Common inductive biases and representations across models. I would say that that's the Mech Interp, like representations across models. Like we're finding, I don't know, curve detectors in CNNs and also in visual transformers and so on, or different across different LLMs, like same kind, similar kind of representations. I don't know,
By the
circles
way,
everywhere. I think that's the one.
by the way, reminding to everyone else that it doesn't have to, just be me and Burnley talking. Like, feel free to talk and don't be shy and comment on things or whatever. And if you don't have to
Yeah.
read the paper, we can go through it. And maybe you have some question or something that some other people can respond.
Yeah. Like at least my understanding of this paper is also like they really want something like thermodynamics of deep learning. Like, like I really like this analogy of thermodynamics where when steam engines were invented, it took like 150 years until we had like theory of thermodynamics. That's like mathematical, and so like maybe there's something similar for deep learning to be found. And here they are like, hey, if we look, it's kinda coming together. Like we have some of these different results, but there's also a lot of critics saying that like, oh, deep learning theory were attempted so many times already, and it never really worked, and so on and so on. So, or like also like one critique that I heard recently, I think it's also good. Is like in like in steam engines, you know kind of what to optimize, like uh, uh, with entropy and so on. Like you can quantify the quality, like temperature. You know that you're looking for temperature, for instance, but in AI systems that's kind of harder. Like what do you how like in order to make a theory in the first place, you have to know what to quantify, which is kind of an issue. It seems much harder in the sense, uh, since you have to define intelligence, for example, and then somehow define it in such a way that you can actually measure real things. But like,
I
at
mean, there are
least
some
it
things
seems
you
to
can
be,
measure,
yeah,
but yeah,
yeah. But it's
you
always
can
so
lose some
approximate.
pre-training.
Yeah, yeah. I think epiplexity is like one example of a like beautiful theory that's very theoretical, and then they approximate it with area under the loss above the last point of the loss curve, which is like I don't know how much it corresponds. It's extreme approximation. That's trying to get to the original idea, but yeah.
In that case, was a close idea to approximate it that way, so I don't know how much to.
Okay, yeah, yeah. No, I mean the epiplexity paper itself is like I think human written,
Oh yeah, no, but I mean
while
the
yeah.
approximating the publicity that way, right? Unless it's
No. That's from the original paper actually.
Oh, okay.
Claude just applied it. Yeah. So, but maybe they used Claude. Who knows? uh, yeah, I think like this is related to Mech Interp in the sense that like I don't know, we were like looking at a paper that was like how features evolve during training. I think there is something like physics of features of like or like in Entropic also like when they showed I think it was in the line breaking paper where they like tried to make a physics simulation of how the features organize into the different circles, for example. So like you could say that's physics of features in a sense. And here they call it learning mechanics more generally, since yeah, it's using a lot of classical mechanics machinery, like kinda. Yeah, universal phenomena. That's statistical mechanics, so that makes sense. For instance, which is applied a lot as well. There are a lot of papers trying to apply statistical mechanics at the deep learning systems as well. Oh my god, there's so much theory, and I haven't read so much. Yeah.
Yeah, I guess this paper also works as a like if you're interested in this kind of theory of deep learning, was just a pile of citations, right?
Yeah, exactly. Like I
Because
think that
I
like
just
this. Yeah,
understand
go
it's
ahead.
mostly not that much, having new content, but much pointing
Mhm.
at a lot of theory that already exists, right?
Yeah. I think that you could. I see this paper as like a big summary and like putting it all on one in one place in
Yeah,
one
more like
language
a
and so on.
literature review, but yeah.
Yeah.
But it's not a
And
literature review
also,
because they are trying to it's also they are trying to make some argument about it, but yeah.
yeah, like the new thing in this paper is at the end the open questions. I think. Well, I'm not sure how much they are new. Some of them already exist, but some of them I haven't really heard. I think before, which is also pretty cool. Yeah, so we can read it now if you want.
Yeah. I mean,
Yeah, at the beginning they also mentioned the five ones.
it's long, so we'll probably have to just kind of skim it. But yeah, let's
Oh, it's
go through
41
it and
pages. Okay.
let's go through it and
Yeah.
like say things that look at things that are interesting. And yeah, people feel free to say something or like I don't know if you want me to go to some section that you think is interesting, we can go there and talk about it. Uh,
Hmm.
Otherwise, I'll just go slowly through the first thing and comment on things that seem interesting to me.
Yeah.
Uh,
Although the deep learning theory is also looking at like activations
okay,
by
so this is
themselves,
just
not really at
the
features.
introduction. Uh, I guess apart from that is probably not that is not that interesting. Papers makes the case that yes, this will be theory of deep learning, that we can see pieces of theory emerging and study the technical mechanics of the learning process. Okay, so that's the thing they are trying to claim. So it's like a mix of a
Yeah.
literature, it's like a part of the literature but they are trying to use the literature to make the case that there is this.
Yeah.
We take
I
this
think
one
yeah.
specifically. Hmm.
Yeah, yeah, it's also like and what are the exact words for it? Uh that new not paradigm, but like hey, do this. Here's what to do this. Like here's what exists, here's what's missing, so now do this. I'm not
Hmm.
sure what's the word for that. There is a word for that, definitely.
Yeah, I know what you mean.
I
But,
yeah.
uh, yeah, so here's later that there is a classical traditions of statistical physics, that kind of thing, but they usually don't really apply to machine learning.
Yeah.
Guarantees
Statistical
when
physics of deep learning.
it became clear
Yeah, classical learning theory.
they were changing structures, representation, and displaying aesthetic in the way of I mean, I think, well, yeah. Uh, Yeah. I think that makes sense. Decision which the source comes from a mathematical study what's possible to scientific research to describe applying whatever predictive behavior compares empirical systems. Yeah, that makes sense. And this relates to the thermodynamics stuff, like how people invented thermodynamics trying to explain better how the motors that they are well already building actually work.
Yeah.
And like what the
I'm
limits, how to
surprised.
make them more efficient and what the limits are and all that.
Yeah, when you understand entropy then or other thermodynamic quantities, then you can much easier steer the model, especially I mean steer the steam engines. So I think
I made
that
them
is the same.
yeah. We should do this approach this task as a scientist embracing scientific. Yeah. The development of scientific field and the development of mathematical one. Yeah, I mean yes, but at the same time I feel like the paper is still like the so far the framing seems to be like things like the table you show seems to be they're still trying to mostly make math out of like yeah do something more like thermodynamics and less like Mech Interp or biology.
Yeah,
They
yeah, like this
mentioned
paper itself is mostly on the learning mechanics aspect, so on the pure physics, you could say. So which is like much like uh like one way how to say it is like but like if you compare it to physics and biology, then like in biology, you study like very concrete structures in the body, like very concrete cells. Like you can study a specific type of a neuron your whole life and just map out all the nuances. I think Mech is in big part doing this kind of stuff, that it's like very like looking at specialized like concrete circuits, concrete features and so on, and much less on like the general rules. Like sometimes it does,
I
and then it goes into physics more, I think.
yeah I guess this kind of the thing when they talk about it kind of if we should look more like the development of scientific field than the development of mathematical one, maybe we should be doing more the Mech Interp thing than the other. I mean, we should be doing both really, but still, like I don't know
Like
how much I'm convinced of like that they were going to get good theories of deep learning anytime
hmm,
soon. Uh,
like yeah, like how I say like this physics part, like if you look like in classical mechanics, for instance, like the objects that follow the laws of motion can be anything. It can be planets, it can be whatever. While so like if you go into Mech-Interp, you could say if you want a physics of features or physics of circuits, then like maybe there are some like general rules of like how features evolve during training and how they reorganize into all those different geometrical structures, like the different circles and so on. Um, so you could say that would be the physics of features and physics of circuits, of how they self-organize, which is not dependent on the exact circuit or the exact feature, but something that's more like universal rules or something like that. That's I wish something like that would exist, basically. Um,
oh, by the way, someone Eric posted a link on the
oh
chat
yeah,
on some physics of
yeah.
language
This
model.
is Yeah, this is another paradigm. I think this is mostly empirical. Uh, I have bookmarked. I don't remember exact details there, but I'm not sure how much of a physics of language models it is. I think it's more empirical, but I don't know. I haven't looked at it much.
Yeah,
Uh,
so these things, there's a bunch of videos and a talk.
okay. Yeah, they're still trying to do that anyway. This is yeah. I like here it's similar. Like th- they they wanna train many models with sufficiently varied conditions to identify more universal laws. Yeah. But I don't know. I don't
Yeah,
Yeah.
that's right. And this is the other approach I'm thinking about. That is more doing, s- looking at models and try to figure out things from the models. About
Yeah.
how, yeah. Maybe we
I
can
wonder if
can
this guy
do a
gets.
paper of that at some point, like on the reading group. But yeah.
Yeah. It's. Yeah. It seems this one also isn't cited, but I'm not sure how. what are the results? One thing this paper doesn't cite is geometry. I send that to the authors. is a geometric deep learning which like classifies different architectures using group theory using symmetries, which is like in physics everything is symmetries as well. Well, if I oversimplify, a lot of things are symmetries in physics. So, yeah, that feels very physics close to me, for instance. And I think that, like, you could say that different inductive biases, because they have different symmetries, that they create different symmetry breakings. I think some papers are trying to look at what I'm saying more formally as well.
Also, here, okay, instead of the Portugal first, they want to say that there are analytically solvable settings in which learning is fully captured by simple mathematics, including limit. Yeah, and there is useful limits. I hope. I feel like the thing I'm very skeptical. Like my priors on any paper about limits is very skeptical because
But
people usually put useless limits instead of useful ones. But
yeah. Like most of the, as far as I know, most of the limit theory is useless for practical models. You could say. I think it's great theory still. But yeah, it depends how you define useful.
Infinite width and infinite depth.
But
Yeah.
there are like some examples, or at least one that I know of, which like, yeah, if you do the infinite limit, you can derive useful properties for practice to scale the models more efficiently. The mu parameterization thing.
Something more easy is that things like knowing that on the limit of infinite width or infinite length or infinite depth, like the models are too incomplete. That's useful, but that's not a super, new or hard to notice limit.
Or infinite context.
Or infinite context, yeah.
Yeah. I think you would trigger some people by saying that it's not useful.
I think I think that limit is useful. Like I think that one is useful.
Oh, okay, you said useful. Okay, I see.
Yeah, or although I think in practice you need to think about what programs actually fit in your actual size, right? But this is more. There are things that people are wrong. A lot of people are wrong about machine learning that are that they think about things in principle that are not true on the limit, so they can't be in principle true. But that doesn't tell you necessarily about what is true in practice, right? But it's more about countering some bad in principle arguments. But anyway, I mean, because simple empirical laws suffice to control my first loss landscape sharpness. Yeah, that's more.
Yeah, the loss landscape sharpness that can be quantified. Yeah. And that's interesting, like, what the hell? Why does the sharpness correspond to 1 over learning rate or something like that? Not 1 over. Learning rate divided by
Or there
or
is
something.
also, in simple empirical law, there is also the most famous one, the Scully loss. That,
Oh, yeah.
and I guess you want the theory of free learning, you kind of have to explain why those kind of empirical laws works.
Yeah.
And they have, and why they have the shape they have.
There's also the double descent as well. Yeah. Which broke the classical learning theory. Intuition.
Empirical laws, yeah.
Wait, you can zoom a bit more for the live stream, maybe.
Okay. Many of the parameters governing optimization can be disentangled and understood. Let me begin a simple, effective learning can change them. As applied deep learning, yeah. I mean, I think there is a lot of things that people know, especially people on the labs, know about paper parameters. Some from just empirical using them. A lot of this kind of alchemy of there is some people
on the labs that have some bias about what parameters to choose. But some things have been getting more over time. I think got more, in some sense understood that like people have at least heuristics and things like that about the parameters to choose.
A lot of duct taped heuristics.
Orientation has convergent best practices. Yeah, like there is, I think there is best practices for the hyperparameters and things like that. Although sometimes it has happened that people have everyone uses some things. I think people used to use dropout and they don't anymore. I know that I don't know that much about the details of training models currently.
Now people are switching to Muon a lot, for example, from Adam W. Because it just works empirically, and Muon is another optimizer that we don't know why it works better to some. Like we know partially, I think, or something like that, but not really fully why it works better.
I mean, there is always a lot of papers claiming that it works, that the new thing or whatever, or like why transformers work better than RNNs or whatever, is because insert explanation here. There is a lot of papers saying different things about that is the problem. Like maybe there is some sense some people know that they have made a paper about it and they are right, but it's hard for that to everyone else to realize that they are right and agree and all that, and the thing to spread out, right?
And a lot of the time, it's just partial explanation, or like in just some certain setting and so on, and not really defined. Yeah, or comprehensive enough. I think a lot of the time they say deep learning works because XYZ. The title is like that to clickbait, even though there's a truth to the paper. Like, yeah, this is part of why it works, but
oh yeah, that's definitely not
not
helped
the
by
full
the
picture.
whole bad incentives of publishing and all that, and like people doing this thing, or like someone publish a new method or something, they doing but the baselines badly and things like that, and their method is always slightly better than the other methods.
Yeah.
Forces mediante interference, greatest. What's in mechanics? Yeah, I'm curious what they mean by mechanics exactly. But it shows how forces acting on objects determine the movement of space and time. Más es more free space, more discrete date. So they want to the science of how the models change, like move through parameter space through the gradient. I think you need that, but you also need a science of what the different points of regions of the parameter space look like and what they mean.
Yeah, I think that's Mech Interp in big part.
And like when, but then I do think you know this. That's a lot of Mech Interp. It's also about things like do the model generalize or not? Like on you need some reason why, some way of saying this is more, this memorization, personalization, or whatever about different points of the space.
Yeah, it'd be nice if that would be more easily quantifiable.
And
other than
how that relates to loss or whatever, and on and positions on parameter space.
There's a lot of correlates with generalization, but yeah, just correlates. I think, which can be used.
Potential intermediate converts to the local meaning of transcript per data. Different, yeah, moment interaction. We can see similarities of instances above always Analytical solver settings to intuition to those learning mechanics. Use limited simplifying tools, those learning mechanics, continuous and statistical mechanics. Motion of a particle. Yeah.
There's also a reason why there are so many physicists in deep learning theory, since it's very much similar tools being used.
Physics is working on spherical causing a vacuum.
Yeah, basically. Those are the neural networks with no linearities that are infinite width or one width. With perfectly distributed data.
Learning mechanics. Okay, I don't care much about how they want to call it or whatever. But so this is for learning mechanics. Okay, so they want it to be fundamental process influential for a first person description on natural network training. That's about so very useful terms, but they should be explained from principles. Aha. Okay. It should be mathematical, making unambiguous quantitative statements about important properties of neural networks. No mechanics is a qualitative sense. Mechanics. I mean, I think we do want qualitative. I guess we need that as a separate thing, right? But I think we also want qualitative statements about deep learning, and they are kind
Don't
of.
worry. In the later part of the paper, they point to Mech Interp and both direction how it relates to the learning mechanics. They separate it, yeah.
Should be predictive, making claims supported by simple, repeatable empirical measurement. We have this, yeah. Should be comprehensive. This is will
Given
not, and should not.
representations.
I'm going to describe everything. I'm a mapper for a portion of the wall where the sits of the wall and the well, say, yeah, that's all science. We want to find the abstractions that compress the data. Learning mechanics should be intuitive, being simple, illuminating, and satisfying in this demystification of deep learning. Like physics should strive for simple insight over technical complexity. Huh.
That's debatable. Some physicists that don't have the philosophy of simplicity, but yeah, that I think it's a big part as well.
I mean, sometimes things are complicated and you need.
Yeah. Sometimes they're just way too
I
simplified.
think I don't like the word demystification because it's usually a way to just say being too reductionist is about something.
Yeah.
Should be
I mean,
useful
as long as
serving
it's predictive, depends, yeah.
yeah. Serving as scientific foundation for applying deep learning physics, thus for other forms of engineering. Like a lot of the failures of people trying, in my view, of papers trying to leave, I don't take about bounds on leveling all that. It's actually oversimplifying the important parts. Like the kind of people who ignores that to make some result that ignores that actual dataset have some structure or they are not random data and things like that. Or they are not, random noise. Should be useful. Will work. Yeah. Should be humble, being sorry what the discussion is explicit about cannot. Yeah, I think that a lot of papers fail at this. I think part of the
Humble.
problem with this is that people want their thing to be useful, but comprehensive and whatever, but their thing is not.
and then they overclaim on the paper to try to sound more useful or whatever.
Also, here they frame it that they want all of those things to be true at the same time, but I think that it is possible that like the more predictive you make it, the less mathematical, or the more comprehensive you make it, the
Yeah, it's probably trade-offs. Although
and
I
some,
guess
like,
there could be
trade-offs, yeah.
Pareto improvements on that. Like that
Yeah.
there are you're doing things wrong, and you make something that makes it better at both. But yeah, in
Yeah.
practice, there is some trade-off between a lot of these things.
Yeah.
When learning mechanics methods will not be easy. It will be sustained effort, both intellectual and intentional. That or Claude 6 will figure it out like next. After thinking for 10 a billion tokens or something.
Yes.
The reasons to seek a mechanics of learning for it to several categories: scientific, practical, and safety related. So intelligence for natural world, yeah. Learning representation of the understand, this has the personal sense. Yeah, this is the steam engine thing.
Oh yeah. Oh, there's some more examples there. Aerodynamics theory as well. I think that's with planes. Much more than engine efficiency. Yeah, in flight. Yeah, that makes sense.
Anyway, stopping a bit. Does anyone want to, say something about the previous thing, or want to would be interested in looking at some other part of the paper in specific that I find is interesting? Because otherwise I'm just going to keep going through this, and I don't know how far we'll get because it's pretty long. Okay, nobody says anything, so I guess I'll keep going. But feel free to interrupt.
Come on, two
People are waiting. I wait.
Eric and Eric. We have two Erics. Both of them are typing. That's nice.
Oh. Perturbation
This is
proving.
cited.
The
Petri. Ooh. A method that generates task-specific causal hypotheses. Huh. That organize on behavior. Okay. This looks very interesting as a paper to read. Circuit topology. Yes. Yeah. They don't mean topology, mathematical topology, but engineering topology, I think. Or do you want to try to jump to Mech Interp and then jump to the rest of the paper? That might be one possible.
Yeah, okay. I think that makes sense. Let's read the Mech Interp thing first, and then we can kind of skim the rest of the stuff. I'm also interested in what they say about Mech Interp. So yeah.
Yeah, I think it's free. It's page
3.1 here.
18.
We discuss mechanistic interpretability, especially because there is a unique opportunity for cooperation. Yeah. I must understand train neural network by identifying the internal mechanisms. Yeah, that gives us to be sure. At its core, this approach scale
Before this, there's a comment on top if you go. Yeah, development and interpretability is singular rank theory.
The critique on like human judgment, I feel like I don't like about it. Look, if you go down for
perspective,
they said how it's like guided by human judgment empirics.
Where? So can you say the line?
Largely a qualitative science.
Yeah, I think this is one critique I have also seen, that they say that Mech Interp is qualitative.
I kind of feel like they're kind of not all
which
of
is wrong, I think. Yeah, I agree.
I think it depends.
This is a common critique.
I think there's more. I mean, I don't think it's a critique. I don't think I don't think being a qualitative science is a bad thing.
Yeah, like I would say like labeling the features is kinda qualitative part, but like I don't know, the modular addition transformer, that's quantitative, I think.
Yeah, sure.
But I mean, I guess an explanation is in some sense a qualitative thing. But I mean, I think if you're only focused on math you are want to do things fully quantitatives. It's like there was this Twitter meme that I don't remember exactly, but it's the thing about we rigorously, I think, of like rigorously mathematically proving an adjacent thing that is not the thing people care about.
Yes, it doesn't end up proving what you want to solve. It'll be able to prove how it works, but you won't be able to know how to apply it to like fix your current use case of not having the models be dangerous.
Yeah. I think both are needed for Mech Interp so that we we don't get lost in the insane complexity.
Yeah. Anyway, so let's maybe yeah.
Yeah, I guess there's also this comment on top, which, yeah.
Empirics. Yeah, it is true that it's often relying on human judge empirics. Like. Will be too low level to answer important questions semantic meaning on its own. Yeah, that's basically true. Like, you can have numbers, but like, if you care about something that you can care about something that relates to what the model is actually doing, and then you like the number can just not be useful, right?
Yeah.
I feel like Mech Interp is closer to the physics versus math, like, or not necessarily.
I disagree.
But we're actually applying it. Like we're the
I
applied
think it's
version.
more like biology, but yeah.
Yeah, I
But
think
like I'm
biology
saying,
is
like
much
we're
more close.
actually applying it and changing the behaviors of the model, and we could do with observation, while the deep learning is more like math. I guess some
Maybe like if you take the brain, like the neuroscience, you could say, as like, which is much more developed science. Like we have like, yeah, we can also probe, like, I don't know, in brain there's a network specifically for face recognition. So if you do ablation there, which they call lesions instead, then like yes, you can change the behavior in this way. And at the same time, the brain is also electromagnetic, also, as in electrochemical. So yeah, so you can use like the math of electromagnetism as well to yeah to do all sorts of stuff with the brain, like electrostimulation, for example. That's like inducing electrical current, for instance, and that also changes it.
So,
So like you can do both, I think.
Here's the talking about when you evolved and how calls for rigorous generation interpretability have been steadily growing, and that their learning mechanics thing could help to provide. I feel like it's still like rigorous foundation of interpretability will not be just about learning mechanics. In fact, it will be more about some. I feel like it's missing some theory of what an explanation is, or something like that. Or
Oh,
what
that
a
will
good
that
explanation of a model is.
well, that will go into philosophy of science, and that's endless rabbit hole. But maybe, yeah, maybe there is something more rigorous than
I
that.
feel like it's less on endless hole in that I think we have kind of in the machine learning models, we have a machine that generates explanations that generates correct models that generalize of things, and like maybe we can figure something out based on that. But yeah.
You mean, can you reframe what you said? I'm not sure
Okay,
if I get it
I
exactly.
think that this is the thing of they talk about here too. They mention, I'll go back to 3.1 first. They mention on that deep learning Yeah. About yeah, I don't remember what it was, but they talk about how deep learning is is exploiting. It's like it's using some truth about like has some about how finding good learning and finding good representations of some data works, and I feel like we kind of can solve the meta problem of interpretability partly by learning more about how explanations work by how machine learning works.
Okay. Like when ML model generates an explanation, like when LLM labels a feature, like how does it work? Or like you mean more generally as well?
More generally, I think like we don't really understand in some sense learning or doing good inference from some data and
Mm-hmm.
how the brain does that. But we have now machines that kind of seem to be doing it. And
Oh, so you mean like if we understand how the machines do it more, then we will also understand how humans do it more.
I feel like and I think that we can.
I think they make this point in this paper as well.
Yeah, they make they make that point in the paper. I'm saying that I think the endless rabbit holes of trying to figure out what an explanation is, or like how to say what a good explanation is from to be able to do things like have a good theory of Mech Interp that lets you say things like when something is a good explanation of some data are actually easier than the previous philosophical rabbit hole because we have in some sense more access and math and empirical access we have to machine learning models and like what explanations are inside what these machine learning models and things like that. Otherwise, what some model of the real world is.
Maybe there's a meta problem. You have to have a science of explaining the explained
But yeah, anyway,
explanations.
going back to the interpretability thing.
Yeah.
We emphasize to completamente formalize core assumptions. Can makes it explicit, formalize, and when necessary the core of the assumptions. Yeah, that makes sense. Linear representability. Well, yeah. I mean, the linear representability somehow, for some reason, seems to work very well. Like it just keeps working, and like there is very few examples of things that we. I mean, that's hard, partly because of methods, but there are very, very good examples of features that seem to be represented non-linearly that we know of. That are in like there is like circles, but that's just kind of also linear. And there is a few things like the phylogenetic tree thing, but
I wonder if the line breaking circuit that seemed non-linear maybe. The geometry of the line breaking task.
I don't remember that one. But
the Anthropic paper, geometry of the line breaking. Wait, I'm sure you do. Wait, let me find it. Geometry. When models manipulate manifolds, where there is
that one.
rotation and so.
But that one was linear though, I think, because it's I know what you mean. I was just confused moment. So I think that's linear because it's kind of it's not linear that it's a spiral, right? But each number is still a direction on the space.
At the same time, like there's also the rotation the manifold, for instance. I mean that's also kind of linear, like linear aspect, the rotation itself. Like I wonder together all the parts of the circuit are linear. Like if all of that is just one direction.
I
I'm
feel
not
like
sure
the
about
parts
that.
could be linear, but the combination is not linear. So maybe the
Yeah,
idea of
that's
like
my
no non-linear features, maybe it's like only true for like one feature
circuits.
direction, but when you combine all the feature directions, it becomes non-linear, obviously.
I think they have
Yeah.
a interesting structure there, but still, it's hard to find examples of some feature that seems to be representing that there is some, I don't know, for example, some manifold that, if anything finds on that manifold, that is just not equivalent to some direction. It's that feature, right? Most things we know of seem to be just the kind of thing that you can find with a sparse encoder. And there is a structure like the thing on the manifold paper is structure that you can't find with a sparse encoder, but there is more about the relationship between the features than the features themselves. So I don't know.
Yeah, probably. Yeah, I
Anyway,
would say that's correct. Like
I think a good
also,
example
yeah,
is the phylogenetic genetic tree thing, but we never did read that paper.
we can read that soon as well.
Uh,
Or like for instance the modular addition transformer, like that kinda isn't a direction.
no, but
If you add
the numbers
if
are
you add,
still directions, I think.
hmm,
Right. Yeah, it
like
does.
if you change
The actual
input
mechanism is
number.
some more complicated nonlinear thing. That's necessarily true, right? But the actual features there also seem to be some.
Even in the Grokey modular addition transformer with the trigonometric algorithm.
Yeah, I think that like so on the trigonometric algorithm, I mean the representations of the numbers have some nice Fourier structure, but I think it's still basically some direction. You can see each number as being represented by some direction in space. I guess this might be a thing where
Now I wanna try steering it then,
a
if that's
general
possible.
thing about what happens if you want to have points in some space or something that
Hmm.
about how the attention works and all that. But yeah.
Hmm.
Anyway, compositionality. I mean, there has to be some actual reason why, and there is we have a theory why. But yeah, like okay. So to see some alternative way to it could work. You could imagine there was the polytope lens thing by I don't remember the name, but there was the polytope lens posing Les Brown some time ago, and where talk about how you should better think about models in terms of polytopes, but that just doesn't seem to be that useful compared to just thinking out features directions in practice.
What exactly the polytopes? The feature geometries are polytopes there, or
Yeah, let me find the thing.
okay, that's actually interesting. Now I can have, I think that's useful actually.
Is this thing.
Polytope is just general, right? Let me see. Geometric object. Yeah, like I think that's actually useful. Like there was also this other paper we read where they had some more general curves to classify all the
I think
different
in
shapes as well.
practice you rarely find that, for example, in some direction, like up before some point the feature means something, and after that point the feature means something else. Maybe that does happen and our methods are just bad at finding those, but I don't know.
So I see
I
the
don't
co-author
know
is
of examples
Conrad
where we know that happened.
when Conrad still was doing science, and now he's mostly AI governance. Yeah, I think.
Yeah. Now he's doing weird things. I feel like I don't know.
In 2019, Lee reverse engineered GPT-2 in his bedroom. That's written on his Wikipedia.
I think I like.
He didn't reverse engineer
understand.
GPT-2. What?
Later
I
on,
got
like they
the-
talk about how it actually fills in the blanks. So I guess those overly
I
pessimistic.
think that was
Reddit-
when they did like their own version of GPT-2 or something. I don't remember when that happened. I remember it was something like that.
Mm. Yeah.
Like
Let's
when
go
they
more
made
through the paper.
Connor Leaching
Or-
and make their own version of GPT-2 because they didn't need an insane amount of compute back then.
Yeah, back then it was co-founded Outer AI to attempt to replicate GPT-3. Yeah.
Planning how Michaud is the pertaining. But anyway, apart from, let's not get into talking about that and go back to the paper.
Yes.
Composition
let's go
editing,
back to the paper.
computation analysis, the composition of simpler modular submechanisms. Yeah.
Hub mechanisms module. Sometimes, not always, but yeah. There's a citation to 9089. What is that citation?
I'm curious about this whole, yeah.
Local versus distributed coding, intelligentsia. That's maybe more philosophical or something.
Planning how Michaud is developed through training.
Yeah, cognitive science. Okay. Yeah, you could say grokking and progress methods is kind of physics like studying, yeah. Phase transitions in circuit formations. Wow, that goes back to 2022.
Scientific cognitive pyramid, yeah. Highly simplified data models. Yeah, I think that's kind of what I complain about most. This about some theoretical paper. Real data has a structure, and like the interesting thing as deep learning is that it will learn some interesting thing that depends on the structure of the data. And if you are
Yes.
like without any structure, you can only memorize things. Like to the extent that deep learning does something interesting that generalizes to other data because data has some structure and it's not some random data points. If you are going a setting where your data is basically random data points or something, you are going to miss all of the interesting stuff about generalization and learning structure and all that.
Or you overfit to non-existing structure.
Expression can be improving information in instrumental mechanics. Control leveling, the lower for the situation by task. Texture improving phenomena. Yeah, that makes sense. I think we can also read now these reasons for skepticism thing, which also seem interesting to me. Unless people want to look at something else. Commentators can be turned deep learning for decades. We don't have ones. No, I don't think that's true. Like, of course, there
there can be a theory. It's not as machine learning works.
You think
Yeah,
it's
I mean,
not true? You mean
the these criticisms
that
are like, if there was some theory, we would have already found it. No, this is never true.
oh
Like, people are
mm,
not that. Like, deep learning is not even that. They are right that deep learning is not at all. And like, even if something old, like, doesn't mean that you can't find a theory. I think it's people get into the someone would have already found this if it was true. There's usually a bad idea that leads to nobody actually finding anything.
mm.
It doesn't mean that it can be
Also,
non-trivial to find or something, but it's like, uh,
mm.
yeah, I don't know.
Also, I'm noticing you're reading the critiques, which is after the Mech Interp already. You
Yeah,
went with
I
these
don't. I
critiques.
mostly got into the like I look at the Mech Interp. I think there's not much.
Yeah, not much there.
There's
There's
not
also the
much.
comment on top, if not sure if you've read it, the development interpretability note, right above Science of Deep Learning, right above the 3.1 title.
Okay.
Yeah, development interpretability.
Several to make a simple text first principle theorems are almost by singular theory. Yeah. Yeah.
Mm,
Yeah, I think
interesting.
any theory of deep learning has to talk about the geometry of the data, right? Sorry, about the structure of the data. Like if you have, if you're doing theorizing in general about, like you can talk about how different geometries change things, but at some point, if you want to understand how, like if you're talking about mechanics, you have to understand what the shape of the place is to know how things will move.
Yeah.
And have a more general theory that is given some shape, you will get this movement. But
Also, I wonder. Yeah. Also, I wonder if there is something like some like more universal shape of a deception circuit or something like that, and if there is physics of that or not.
and if you want to say something interesting, even about LLMs or something, you'll have to also be thinking about the structure of language or something like that. Or
Yeah,
structure
yeah,
of
yeah.
internet text.
Yeah, like in that one paper, there was a that yeah they literally first learn some engrams, then they learn some syntax, and after that they start forming the features, and the different. And after the features, they start forming circuits. And that wasn't in the paper, but that's how I extrapolate. And and how the features are also arranged in different geometries. That also wasn't in the paper, but it's in the anthropic papers, for example. I really wonder if I think there's physics of all of this, of like given the some geometry in the training data.
Yeah.
But in order to learn the geometry in the training data, you have to do machine learning. Maybe there's.
Yeah, I do agree with this thing by the way here. Like, yeah, developers major sizes can take at least several decades. They have, yeah, I feel like the people. I do think that it's true that there are people who have this kind of objection. Like, this is like just the machine learning brain people who are like accustomed to things being completely revolutionized every few months or something.
Oh yeah, that is definitely machine learning bias. Oh my god,
Like,
this changes everything every day.
yeah, I don't think. I think we can probably. I do agree. We can probably figure out some theory for 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 better literary theory, and it's just kind of hard to do, and will take time.
Mm-hmm.
So I
If
think
you're
yeah,
on
it's
Twitter,
quite funny.
the bedrock of AI is being revolutionized every few seconds. Yeah.
Yeah. We're at the point that I feel like there's people that
at this point also the opposite that it's not actually every few seconds, right? It takes even in machine learning, capability stuff, things take months to progress, and
Yeah.
or a year. And if it's kind of the attitude on Twitter where people like start saying that deep learning is dead or something because there was not a huge development that completely changed everything on the last few months or something. I don't know. People, I saw someone saying that I don't know deep learning is slowing down now because it hasn't been like the change from GPT 6. Sorry, for Claude 4.6 to 4.7 is not that big or something. I'm like, what are you talking about? Like, compared to the things on the end of the year, I like, I don't know. Like, if there is no, if each model
Yes.
release is not completely revolutionary, it's not, yeah, no.
I had exactly this argument with someone like a week ago.
Maybe I
Yeah.
saw it on your Twitter responses, so that's true.
Yeah, this was in the Discord account.
Meanwhile, on
And this
the
was
benchmarks, things are just. Oh,
Wasn't
I
it on a
said.
recent sort of dorkish podcast that they said that they were arguing that a lot of the problems was that they couldn't really scale sparsity and scale, model size due to just how the GPU was oriented at this point?
Oh, that's yeah. I think they. I don't remember something like that. I think that's although I think the Epoch AI people were saying that I don't know actually about the math of that enough to comment much on it, but about how that was they didn't have the enough GPUs for that before, and now they do, and they're probably training bigger models or something. I think another thing is last year people also were scaling, spending more time trying to scale with reinforcement learning that turned out to work better in practice.
yes.
I could see an argument why actually that was more doing more benchmarking than other things, and like you that actual improvements still come from scaling models, and that's why you only saw big jumps in actual usefulness at the end of the year when they made actually bigger models. Because I do think the latest models, like in December and November and all that, were maybe bigger. Being Mythos is also probably bigger.
And hard to
But
serve because of that.
I don't know. I feel like so if 5.5 5.5 Cyber is what they're competing against Mythos, but they're able to serve 5.5 to like a lot of pro consumers. Doesn't that suggest that it's probably not that much bigger for OpenAI
Oh,
specifically?
OpenAI also has much more compute. As far
That
as I
is
know.
true.
I don't know. I
Or,
no. I
yeah.
don't. I think that 5.5 might not be bigger. For things that Sam is saying, but at this point we don't really know, and we are just speculating based on vague things about things that the people from a company say. It's kind of hard to know.
There was also some paper trying to estimate model sizes from extrapolating some scores on some metrics, which got destroyed. That it's not as good. But yeah, so that can also be used, and I think Opus is like bigger. I think yeah here. So yeah, Gemini is the biggest apparently, and GPT-5 is this is relative to the previous.
Yeah. I think the thing is also like
But-
going to the progression deep learning stuff. Like they don't get like building more compute takes time. I think part of why the current models are better than a year ago is because they have a lot more compute. A lot of that's a lot of why. And like they get more compute kind of they don't continuously get more compute. They get more compute when there is some
for training. They
Mm.
need really big data centers, and they take years to build, and now they take like 1 to 2 years to build, and now they are getting the ones that they were building last year, and they are still finishing building them now, and they're starting to get operational. And some of the biggest ones, like they don't want to get the biggest things like until the end of the year or something. So, and I think that a lot of this, I don't think things like before a few, like 1 or 2 years ago, people they used to release less models, right? They didn't release models as often, or they did, but they all did it quietly without calling it a new model release. They did, they just call it GPT-4 still or something. And over time, they started, releasing more models. And so we see more in the intermediate steps, so it feels more things. But when you look back at like I don't know how models were like a year ago or something, and then a year before that, the rate of change didn't really slow down. Maybe it goes faster or something. And I mean, it depends on how you measure in terms of benchmarks or whatever. But you also can measure if you measure in terms of how much money are people willing to pay. For like the revenue of the big companies that seems to be growing exponentially, kind of consistently. Yeah, I know it's hard. The problem with that is also like feel like how useful it is for people and what the vibes people get of how smart it is on something. It's very non-linear with other measures like benchmarks or something. So
Yeah,
like you can have a thing where it's 90% and it goes to 99%, and like 90% is not very useful, but 99% is very useful for that application or whatever.
Okay. And also hitting a wall because it doesn't go over 100%,
Well, that's true of the benchmarks. But there's also the thing that I think the thing that shows on something that shows on the meter thing is that the meter metric is exponential, right? The thing with the meter metric, and I think this explains a lot of things about other measurements, is that the thing they are measuring is the difficulty of task, right? When you look at the same data set that they are using, that's the thing that Bruni showed a graph with like how they are posting a lot more models now.
And exponential.
Wow, that was a long time from GPT-3 to GPT 3.5.
Yeah.
So yeah, the models are not a big change, but that's because they just they took a whole they took a year between GPT-2 and GPT-3, right? And it's like now they are just posting a lot more. I feel like people on Twitter get the impression that things are slower just because they are posting more, and they are comparing to the big memories of like they used to post models that were bigger changes from the previous models, but that's because they took a year to do it. But what I was saying about the meter thing. So I was saying about the meter that they measure. My take on is that they measure like how difficult the tasks are for humans, and so that like the difficulty of task cloud grows exponentially, right? But if you measure as percent of the tasks on the dataset, it grows linearly like all of the other benchmarks. I think this is a general fact of benchmarks probably that the reason why, even though you throw exponentially more compute to a task, you get like the lower loss you get and the higher percentage of benchmark is logarithmic, is partly that the like benchmark getting 10% better accuracy on a benchmark gets exponentially harder as you increase like from 10 to 20% is much easier than 80 to 90%, because you also have like I think this is related to things like Thip's law,
Yes. This is the first thing that LLM plan as well, zip flow.
which is the this thing.
Power law for usage of words.
I think there is something like this, but for like difficulty of task or something. Right.
Yeah,
And-
power law for difficulty of task. I think that's correct. Well, in math, at least, Terence Tao said that like the distribution of open problems in math follows approximately power law distribution, and right now all of the LLM automation is like picking up the easy low hanging fruit on the tail. So
Yeah, but anyway, I think I kind of getting sidetracked, so I probably should go back to the paper. We can talk more about this later.
what's the option?
I don't know what people want to talk about.
And I think that this yeah, I think this distribution that Terence said. Oh yeah, I found the quote. It's true for basically most task domains, and like anytime it's verifiable, then AI can like in its current state can.
I guess the
can
last thing I say is that
can
it
just-
does seem possible to me that there is something about maybe it turns out the actual that spending a lot more compute on reinforcement learning is a distraction, and the thing that really makes the model smart is making them bigger, and there was actually some slowdown in 2025 because they couldn't make them bigger for the things that they said on the Dwakesh podcast, which was that file said, but I don't know, and I don't think we can really figure that out. That
Well,
I think maybe we can figure something out. I kind of want to ask Claude later to look for it from like DeepSeek publicity. Like I'm curious about things like did pre-training really like did the scaling laws in pre-training slow down or not? That maybe are possible to figure out from things like whatever DeepSeek posts. I don't know if DeepSeek actually released that information or not. But there is some open source models or open weights at least.
what
But like
information exactly you
they
mean?
publish papers. Like what are the scaling laws for correlate? Do the previous scaling laws that people talk about still follow for pre-training as you make the models bigger on the current regimen where they are, bigger than, I don't know, 1 trillion parameters or something?
Yeah, I don't know about the scaling laws there, but I semi-read the new DeepSeek paper on the V4, and yeah, they show the architecture. Yeah, I'm not sure about scaling laws. They specifically constantly flash how efficient they are. Like, yeah.
Anyway, going back to the paper because I kind of think, this kind of was a side thing of the.
Yes.
Oh yes, current understand material primitive compared to them. Sorry, I feel pretty understand of large models is too heavy a lift. Yeah. Understanding of the basic building blocks of deep learning will probably be useful for the constitutive theory that explains the whole model. We can see this happening already in isolated pockets, including empirical scaling laws. Yeah.
Mathematical prescriptions of hyperparameter scaling. Neural tangent kernel-based methods for data attribution.
Legal theory, small pieces of the learning stack are used for parameter scaling on large models. Yeah, I think there are some things like that. Like people these days do have some at least vague heuristics or theories that are probably some approximately true in some ways.
Like they don't seem to cite here, but that's the thing I was mentioning, the MUP. That's also like hyperparameter scaling. zero should transfer between small model and big model by making sure that the hyperparameters are stable as you increase the network width in the limit, and there's still meaningful maximal feature learning.
Identification with the basic objects in a field of science that makes it possible to ask applied questions in a more sensible way. Yeah, I guess that makes sense.
Yeah.
I was thinking, yeah, this could be some theory thing. Even if it doesn't explain something, could maybe be helpful for some things on Mech Interp. I don't know. It can also be. I think like a lot of the existing theory stuff is kind of useless. But
That's I think correct. If you
But I
define-
think they also agree with this, and they have some reasons why a lot of that is useless.
But I think I think the most criticized part of deep learning theory is categorical attempts. Category theory is too abstract that it doesn't really give much concrete predictions. Models I think I disagree.
Yeah, or at least depending on how I feel like there is a big.
I think both are important. It's like with biology.
Make compatibility the biology. I mean, yeah.
Yeah, I think also mentioned in this paper, like the Mars levels of analysis. Yeah, you can like you look at all the different levels of abstraction, very low level or very high level of statistics.
We don't need
for
a
instance.
theory of deep learning with a theory of data. We think we need to understand a theory, structure the data, and theory how the model learns it. Yeah, I get that.
Yes.
Makes sense. I feel like that's the thing we were saying earlier. That theory,
I feel like a theory. What deep learning does is a theory of both things.
Yeah, I think I agree.
If you have if they are aiming for something that like is, I guess you might need something about given some data, some structure of the data, you'll get something. That's a useful thing. Although if you want to know things about that, you'll also need a theory of what the structure there is usually on internet data or something.
Yeah, this is exactly how the geometric deep learning works. It's like what are the symmetries in the data? Let's find them and then put them into the inductive biases in the architecture, and that will make it learn better.
Maybe this I actually I will understand itself before we do. Why is still with you? This is a present concept for human intelligence. I mean that's true. There are three parts. First, theory is already useful and will continue. I mean there is no point in not try to do it now while Claude 6 can't solve it. But yeah.
We will just steer
AI
Sherbots to do
working
it.
in Florentin will show you the separate solve this linear theory. I think actually that is likely to happen, but later. In a transitory. I mean, that's true. Will come from humans this using working AI. I think this is true, but I worry that the transitory period might be like I don't know, 2026, 2027 rather than 10 years. So I will see. Depends on how fast things, deep learning progress in the next few years. But
maybe it will continue being jigged enough, jigged, but maybe not.
We're going to see safety. Some human oversight of AI systems will be necessary, and having a human parsable theory of deep learning will give us a foot on the door.
Yeah, I mean, I think it's more. I think the eyes could. If you have the eyes that could figure out theory of deep learning from the scratch, you could ask them to make a human parsable version or something. But at the same time, that kind of relies you on trusting the eyes, and if you don't trust the eyes, you're already fucked in some sense. If the eyes are doing the thing, and I guess the solution to that partly is actually have a theory of deep learning and of of the safety or whatever before the eyes can just do all of the work, and you are basically relying on them to be right, or not. Having sneak some subtly way is wrong. Also, maybe things like the Paul Cristiano's work, whole debate and whatever, and all of these posts on ways you can use AIs to supervise your AIs and hope that there are things where true it's harder to mislead humans than to say true things in some formats. Like debate or whatever, which I don't know is actually true. I feel like there is evidence on that on the current problems with trying to get LLMs to do good research that generates a slop that is very hard to verify.
Yeah, the verification is an issue.
But maybe it's a thing where with better models, the models will be better at pointing in a easy to understand way what the flaws are or something. I don't know. Operations in learning mechanics. Yeah, I guess this is an important part of the paper. What are simple solvable models or genuinely deep non-linear learning? Yeah, that's the related to the Mech Interp stuff. He said, yeah. And learning mechanics. Yeah, so people understand linear stuff from what I see. Like there is a lot of theory of that. Kernel methods. And the second, layers on linear functions of the data. With yeah. Can we if this is a class of solvable model that causes both linear extended and nonlinear function learning? I'm not sure I understand this
Deep,
part.
nonlinear, and nonlinear function. Are they referring to neural operators?
Here they talk about
Maybe?
deep linear networks and kernel methods. And they talk about this being, more simplified solvable models. And they first that
Yeah.
deep linear networks captures non-linear dynamics of the parameters.
I think that nonlinear functions of data. I think this is from the neurotangent kernel theory. There is some mapping like that. I think. Like
I don't know. I don't know enough about
if you go to if you go to infinite width, I think it corresponds to a Ghosh process or kernel or both. Yeah.
Yeah, I don't understand this the linear networks.
Like-
I don't understand this.
Like if you go into infinite width, you have some correspondence with some other mathematical structures. Gaussian processes is one of them, and then you can do math over on top of those, and it transfers
And
in the
why
infinite
does
width
it?
limit.
What is the non-linear dynamics of the parameters, though?
The fact that the parameters, if you change one parameter, the whole network is non-linear in the sense that changing isn't determined
if they
by
are
that one.
don't deep linear networks, why is that true?
Oh, okay, that's what you're confused about.
Yeah.
I think because the networks themselves are not linear because there is no normalization or ReLU and so on. But
Yeah,
it's non-linear dynamics of the parameters. Okay, I'm also confused actually.
Yeah, no. If they are deep linear networks, are they linear? Like, why are there no linear dynamics of the parameters?
Okay, I am actually also confused there. Oh, I think it's some theoretical reason that I'm not seeing right now.
And kernel methods apparently learn linear functions of the data.
Yes.
Which I guess
That goes more into the functions.
When you change
Like if you go
the data, it changes non-linearity of the
Yeah, I have some vague. I didn't go as deeply into the market, just through some summaries, and you are looking at the all possible ways how it changes the parameters, something like that. Like you go into function space instead of just
Maybe I need
the
to read more
parameter
about
space.
those stuff, but at the same time, I don't know how much. Maybe it's better to just wait for them to come up with a better theory that actually explains deep learning and not.
Like the tensor programs are based on the Nerotanga kernel. Well, it's generalizing it as far as I know, or something like that.
Well, the one
I have a lot of holes in this direction, and wanna look into it more. But yeah,
Okay.
that's too many
Something
things.
interesting is why would a theory capable of capturing new natural data look like? Okay. Let's put it with natural data. This method someone was entering our theories. Yeah, that's the thing I was talking about. In case models derive the
Oh yeah.
from statistics. I think it's not true always. Often, actually.
Hmm.
People are living. I mean, it's once we went have been here a while, but yeah.
These
I mean, people want to say
different
something or like
tables
want
can be.
to be, look at some specific
Yeah.
thing. Just
If you have any
say
thoughts
that.
about this paper, for example, you can say, or any additions or ideas.
Some notion of functional complexity. Huh. Some precise notion of complexity among functions with low loss. What is the approximate notion of complex? Yeah, this is the thing. Normal circuit with norm or something else. Like there is some sense in which
Complexity.
models find simple solutions, right? I mean, part of it is just weight norm, but that's because we use regularization on the loss. But even without using regularization on the loss, models do favor simple solutions in that.
Yeah, there's still
In the Grokin
simplicity bias.
paper, you can remove the so that you can get the generalized solution even after removing regularization. Just takes longer.
Yeah. Flatness of the loss landscape is another approximation.
Yeah.
But it doesn't work always. There is some paper saying that sharp minima also generalize. So it's like correlation, not
Yeah,
causation.
that's the thing
Probably.
about
I don't know.
how we feel like the theory has to partly be about things like what do different shapes of the loss landscape mean? Or
Yeah.
how generalized solutions, different kinds of solutions to a thing that with different generalization properties are distributed in parameter space.
Singular learning theory tries to look at the geometry of landscape and generalization.
To the extent that machine learning works, it has to be that the case that there is some relationship between the shape of this of parameter of gradient space on like what the loss landscape is, but to generalization, right? I mean, obviously, lower loss, like things that generalize will get lower loss, but things that memorize also get lower loss, and there has to be some reason why you find the ones that generalize, which might be some combination of, maybe there is a bigger region with the generalized solution, or maybe just the memorized solution, there is just few points in the space that are like that, and so you are less likely to end in there, or there has to be, a bunch of reasons why, and yeah.
Mm-hmm.
The theory of generalization has to be something relating, the shape of the loss landscape and how deep different optimizers move through it, and to properties of where they tend to end up in.
Hmm.
Not properties of generalization. Yeah. Features learned by neural networks.
Also, there isn't spline theory, I think, in this paper. Do you know spline theory of deep learning? Which also tries. Wait, let me see spline. No spline mentioned. Okay, so it's missing geometry deep learning and spline theory, I think. Yes, that one tries to like see how the different layers decompose the data into different splines, which is a certain mathematical structure, and this way they found that like if it's very scattered splines, then that's less generalizing. If it's very smooth splines, it's more generalizing. Like plastic. The metaphor there is plastic origami. That networks are plastic origami. It's very cool theory. Elastic origami. Well, that's also plastic, whatever.
Finite neural networks properties understood. That's an interesting video. I could watch it later. As a
Mhm.
approximation to infinite limit. Maybe.
Uh, Wait,
Discretization hypothesis.
infinite
We
limit.
say that finite neural networks are simply discretized approximation of infinite networks. I don't know if this is true. I guess I could see that section. to
Oh,
see
interesting.
what
I
the
didn't
grade
know that
is.
aspect.
For the
Yeah, that
limit
makes
put
sense.
inside is the measure of Liberty Headless.
Oh, that's a cool cool correspondence. Wow, okay.
Model type.
Yeah, that makes sense. That makes sense.
With the, I don't think that actually is that very good of a way of finding the thing in that the increasing model size does other things. Like as a simple example, if you or like you can see as video approximation, but like if you think in terms of making term, like obviously there are things that if you on bigger networks, there are things that don't fit on the smaller networks, and also
Yeah,
in some
that's why
sense,
discretization.
yeah,
Since the more you discretize it, the less space to encode data you have, the less granularly you can model the data set or form general representations from reinforcement learning.
I feel like this can be an awkward way of thinking about a bunch of things. Like it might help something, but it's like.
I think it's kind of similar. Like this is common in physics. Like you always have discretized measurements, and you assume continuity, and this way it also simplifies your math sometimes. So it may be useful sometimes, but depends. It can be completely useless sometimes as well. Depends. Yeah, I think. Ooh. How does
Probably
loss
this carry less
correction?
exponents a priori. Yeah, that's the usual. Does anyone does that? I don't think so. It's still related in the dataset. What's the dataset to the dataset?
They do not appear to be simple fractions.
Yeah. How does Ghosh Corbett interpret with? Oh, well, people are leaving.
Hmm.
Uh, so Learning mechanics. Yeah, well, this is the experiments frequently is just the recommendations. So there's a robot mission in deep learning. Do large model, and this is an interesting one. What sense do large models train differently learn similar representation?
Yeah, by the way, in terms of this, have you seen the Aristotelian representation hypothesis?
I saw that you posted it, and I put it on my saved stuff on Twitter, but I haven't read it.
Oh yeah, we could read this one as well, potentially.
Yeah, I see. In the development of learning mechanics. Yeah, no, this is yeah. In what is the universal? How does a similarity? Does it compare hit dimensional representations? That makes sense. After that, okay, what? Curious about a thing here.
The loss curvature is interesting. I really want to read that paper that says actually sharpness also generalizes.
I talked to Mech Interp people, which I was rather looking for.
Clement Domingue. Wait, no, that's a different one. Jesse Hoagland. So that's the singular learning theory person.
Isn't anyone quite special I recognize?
This is cool paper, but it's incomplete. I wanna expand it with geometric deep learning, spline
With the
theory,
people they asked
and
feedback from, I feel like it's kind of
category.
legit.
Oh, say again?
Makes sense. Like Jesse Hugulin gave feedback, so they have an interest in like how the model learns.
Yeah, Jesse is on this intersection of Mech Interp and biology of LLMs and physics of LLMs. Well, or deep learning.
I guess this is
generally.
Jesse's view of how LLMs work, kind of.
Like my view is also very physics based. I think. Like I believe there is something that's like physics of features, physics of circuit formation. Like that's a field that's just waiting to be developed. I may try, but I will need so much more math to learn and so much more practice.
Jalle Kun,
to-
when
and so
back
on.
when Jalle Kun did actually useful stuff.
I
Well,
think
don't know if
actually the
useful.
JEPA, like I think JEPA is useful. I just think it doesn't make all LMs useless or hitting a wall or etc etc. Like JEPA is a great paradigm. I think energy-based models are very interesting. Like and it will also be, and it's more interpretable. JEPA is more interpretable because it depends which JEPA, etc., etc. There's variants, whatever. But like some of the core ideas there is that you learn these latent variables much more explicitly, and this way you can causally manipulate the latent variables much more. So like there's like causal JEPA paper, for instance, where you predict the next latent variable in video space. Therefore, so like, and the latent variable can be like a circle, or a ball, for example, in a video. So you have like balls with different positions, for instance, interacting in a video. So like they can bounce and so on. And you do there's like encoder that takes the pixels, transforms it into this latent, and then you predict the next latent. I think it's great. It's more interpretable. But maybe Bitter Lesson will steamroll all of this. Yeah, there are some more attempts at interpretable architectures.
Yeah, I think
What's the name?
discretization is.
Oh, go ahead. I was just asking the
No,
name of the paper.
say whatever. I will. I've been talking for a long time. I kind of want to other people to say something if they want to.
Oh, I just joined. I'm just curious. What's the name of the paper?
Oh, so
They-
this is there will be a scientific theory of deep learning paper, which
Oh,
is what it says on the thing. So they are trying to argue that they have a bunch of. It's mostly kind of a literature review thing with a side of trying to convince people of working on deep learning theory, and where they talk about. Yeah, they talk about a bunch of things about what the existing research theories are and what they are missing, and they want that to be some mechanics of learning, and they talk about a bunch of things about how that would look like, and finally they also mention how this relate to Mech Interp. Like there's a 3.1 section that we already went through that is about how this theoretical idea relates to Mech Interp. Basically, yeah, a bunch of that. It just says a bunch of things, but it's mostly talking about what existing theory is and methods and all that.
Mhm.
Yeah, I think it's a really good paper still, though. Yeah. But I would since I don't know, since one of the things that I love doing is mapping all theory, all Mech Interp, etc., which is why I started the Mech Interp wiki, for instance. So this is kind of mapping the whole, not whole. There's still missing things, a lot of theory of deep learning, and connecting it with Mech Interp as well, which is cool. Well, in my collection of collections of deep learning theory summarizations and or science of deep learning, this will make a fine addition to my collection.
Okay. Anything else anyone wants to look at? I don't know. You can also just finish the paper because I mean there's a bunch of theory things here.
Yeah, I
I'm
haven't.
not sure how much
There's
it's
if you
worth
want,
it.
there's universality across architectures, for example, which is Mech Interp related as well.
What is that?
It's the 2.4. They talk about hyperparameters and then descent figure 6 universality across.
I guess I can go show this. Yeah.
Yeah, we can search for this. So this is universal phenomena across different architectures and data modalities, and they show example of diffusion models. Figure 6, especially if you go down a bit, or if you want to read this part as well.
Then when you have ephemeris modes, yeah, if you double the learning rate and the batch size and halves the number of optimization steps, try to stage linear shapes.
Yeah, that's exactly. Oh, okay. This is related to the thing that I was talking about. There's a lot of invariances like this. So, like one analogy there by the authors, which I really loved, is like, when you're building a bridge. Let's say you wanna build Golden Gate Bridge, then like you in practice you cannot really build 100 bridges and see and 99% of them collapse. So like if you can first build these small bridges and then use the different invariances to scale them to the bigger bridges and make sure the material science properties are preserved, aka invariant. Therefore, then you can do much better engineering basically, and also controllability and science and so on.
And were they able to do that yet, or this is just a hypothesis?
No, for transferring hyperparameters from small models to big models, that's all was done, and for GPT-4 did that, for example. At least they cited tensor programs in the GPT-4 technical report, and then some person on Twitter said that we probably used me-force, something like that. So I think it's kind of obvious, but it still might be wrong. Why would they cite tensor programs? Because the tensor programs literally explains how to do this zero-shot hyperparameter transfer using this infinite width limit. Like they looked at like, okay, if we want to make sure that the activations don't blow up, like are stable, so so like there's still feature learning happening. So like yeah, they don't blow up and they don't die into zero. Like that's lazy regime, I think. And then if you do that, then like if it's still stable while you're increasing the width of the network, then you're good. Also, there is a variant for depth of the network, so it's also for that. It's not just width, but also depth. So
And also, optimization parameters in deep learning affect not just the speed of training, but also the trajectory that training follows. They need to affect various properties of the layer network, including generalization performance and compressibility. Yeah, that makes sense. So, explain has to express through the hypothesis that many prefigured persons and parameters can be understood as implicit realization of Lor's function curvature. That makes sense. Oh wait, why is my selection thing broken now? Doesn't matter.
Hessian, yeah, curvature is called Hessian, right? I think that's just a fancy name for like second derivative of the loss function. I mean, yeah, that sounds good. Let me see. Yeah, second order partial derivatives of the a square matrix of second order partial derivatives of the scalar varied functions. Yeah, it's just a fancy name from vector calculus or multivariable analysis.
And the first order was the Jacobian, right?
I think so.
Yeah.
The Hessian matrix of function f is the transpose of the Jacobian matrix of the gradient of the function f. The Hessian is equal. Hessian of a function is equal to gradient, the Jacobian of the transpose of the Jacobian of the gradient of the function. Ah, wait, interesting. Wait, gradient is ordered, the one derivative, and Jacobian itself is first order partial derivatives. That makes it the same in terms of orderness of derivatives. Or am I mistaking something? Like gradient is just first order derivative, right?
I think it's the inverse of the.
No, the gradient of the Jacobian is what you're taking the derivative in regards to. So I think
Right, okay.
You-
Alright, okay. I see. Yeah, this is for for all the x's. And this is for x and then xj. Uh-huh. You get all that. So you get that, and if you get the Jacobian matrix, you get Jacobian FF is this. Okay. Yeah, I see. Thanks. Empirical studies ensures first regularize the curvature of those family flare. Yeah, if you wanna look at the universal or if you're still reading this part, I like this part as well. I think like I watched the podcast with the people and read some of the paper, but still not in full. And I'll read more of it with you basically now. And yeah, I think I'll read the rest as well. Yeah, 10 supergrams mentioned. That's what I was talking about 6 billion times. Yeah, here. This is very interesting. Like diffusion model architectures converge to the same line distribution and produce identical images. This is kind of the Platonic representation hypothesis, but not really. Like it's one data point out of many. Have you seen this, by the way?
No.
Mhm.
Different diffusion model the same level distribution. Oh, that's interesting. The internal representations become increasingly similar to that of vision models and more software models.
Yeah. Yeah, here they talk about the maximum update parameterization. Since μp is the scaling to use, how to scale, and it gives you how to scale the hyperparameters with the model width. And you can do the zero-shot transfer. Yes. Exactly. This is the best result of theory of deep learning that I know.
I see.
In terms of practice.
So
Practical application.
this analysis is
And by features, they use features. As I think that's just the activations. They just use it. Non-trivial, not exposing, not non-explosive scaling is GIF. That's good. Like, I'm surprised it works. Well,
yeah. Diffusion. Yeah, so it doesn't matter if your contribution less than transformers in computer vision. Or like, yeah. They fed with the same noise.
this
sensor.
is very much bitless and pills. Screw your inductive biases.
Despite the pet defense, as part of the responsible showing intelligence toward archaic activity geometry leads to accurate quantity precision. Okay. Enough precise standardization on computer material data with a conversation is not possible. Yeah, this is the thing that yeah, I feel like there is a kind of paper who says that machine learning doesn't work because of something like this. That is, people keep
Is
reinventing this
Is the
argument.
no free lunch theorem mathematical or just
No, it's math. It's
conjecture?
true, actually. It's just
Hmm.
about random data. It's about arbitrary data.
Mhm.
And kind of trivial.
I wanna read the proof, and
Uh,
it's 20 years, 30 years old theorem. Oh wow.
it basically, if I remember correctly, basically says that, or like the one they mean, there is a bunch of non-freelance theorems, like it's like common name for theorems, but like it's a basically the common experience basically says that on the any optimization method or algorithm will will have this the same performance on average over all possible data sets or whatever, like of tasks. This includes just picking things randomly. Nothing can do better than random. You can see like an intuitive. I will use math derivation, but as an intuitive way of why this happens is that you can always imagine, if you imagine some data set where you see some data and then the correct answer is something, you can always imagine the versions where the correct answer is the opposite, right? But when you are thinking about that, you are already on the outside reality in some sense, that we don't live in the set of all possible problems or something. We live in some specific universe where data has some specific structure, right? And this is the thing of deep learning must rely on particular features of the data present across all data and modalities on which it sits. For instance, many cases of images and audio signals share power, loud spectral properties, sparsity patterns, multi-square sets, etc. Can be analyzed with general processor wavelet basis. I don't know what general processor wavelet basis is, but okay.
You don't know what?
What general processor wavelet bases are. But okay.
Yeah, that's from Fourier analysis, I think.
Okay. A similar parameter test is the we talk about this Zipf's law. We're thinking about a proper large distribution. The hosts are made in natural and artificial languages. Hierarchical computer structures are used to model both image and text, computer related through a common model. A single learning algorithm to tackle similar related tests, leaving only the finite grade differences between them to be learned.
That's very interesting.
Yeah. Going deeper in the internals of the network, it has been said the representation layers of different levels can be similar. Yeah, this also we talk about the whole representation, platonic representation stuff and all that. And shown that networks and that Aristotelian representation with the positive thing seems related, that we'll have to read to see if this lop are actually interesting. But yes. I guess I'll skim it before deciding if we read it or not. By the way, talking about reading, people feel free to suggest papers to read that you find interesting on the reading group channel. Otherwise, I'll just pick whatever.
Yeah.
Like I don't know what.
Maybe next time, if Roundbirds, if is he still here? If he wants to present his new paper.
I think he already said that he doesn't want to do it like next week because he wants to polish it. But yeah, at some future he can present his paper. Yeah.
Yeah.
Also, there was someone else that Renberg knew that also could maybe present on the future, but Renberg was telling him to, and he hasn't done it yet.
Maybe we could read the polygenetic thing.
Yeah, that's another one.
Next
also,
week or something.
If there is, which is also if there's only one topic thing or something, but yeah.
Let me see the universal representations. Can be similar, yeah, they say similar. Initializations with architecture.
on the range of yeah,
This
not
is
fully
so
known.
cool.
But
And
because
also-
the result is because of the chosen comparison makes our similarity. Okay, that makes sense. Which representation mirrors or should choose in difficult circumstances and highlighting the cases where they can be unified. In the mechanism in this university, the behavior of many systems should depend on the features common all system. That's true. That the more similarities there are between models, the better it is for some general theory of deep learning that needs to rely on different things, so less things. I said, it tells us the primary reference of the structure data. I don't think it just does that. And also that it doesn't help with reinforcement learning, I think like that. And
what exactly you think is wrong?
no, I don't think it's necessarily. So, if the internal structure of trained neural networks primarily reflects the structure of the data, then studying neural networks might be studying the structure of the data and generating processes.
Yeah, I think it's true partially. So,
Yeah.
like what is the structure of AlphaGo for AlphaZero, for example?
And there might be
Yeah,
some
I think for
dependencies on the architecture, and it's not fully all determined by just the data.
Yeah,
I think,
definitely.
yeah.
What do you want to say?
Oh, I was just gonna say, I think specifically, like you were saying, for certain things like biology, where there's underlying it fundamentally a really, really strong physics constraint, like you were saying with AlphaFold, or I think that those are probably going to be pretty. You're probably going to find a lot of representations that are going to accord with some sort of underlying biological reality.
Yeah, there was Mech Interp on biology models, and it found various
I think
corresponding
there's a thing where
structures.
you'll have similar structures in some representations, but on things that are more like the kind of thing people try to improve informal learning, all that. The things that are how the model solves tasks, it might be different. For example, there is a bunch of models like this related to the modular addition stuff, where there are some papers finding that there is different mechanisms. It was the pizza algorithm, the clock algorithm, whatever. But they
Yeah,
were
the modular addition.
they were both using the same representations of the number. They were both using the same spiral kind of thing, right? But the actual mechanism that used the representation was different. So I wonder if there is something like that where there is multiple way of doing things often, but the representations on the model a lot of the structure will depend on facts about the data, but things that are less about representing the data, more about solving some task, will be more different and depending on the architecture, because tasks can be solved in different ways. So yeah, in the case of model,
there's also
say
there's also the pizza and clock algorithm thing.
Yeah, that's what the thing I was talking about. That both the pizza and clock algorithm use the same representation.
Okay, but it's in different ways.
Yes. So maybe you can do you train models and you find that they end up, for example, doing modular addition in different ways, but they all end up representing numbers as a spiral because of the symmetries and stuff that we saw. There was a previous paper about that, and the kind of thing Colin Pans, the kind of thing that they show on the anthropic paper, like the manifold paper that you linked earlier. The counting, the line breaks thing. So the line breaks thing, they have reasons why it makes sense to represent the numbers, as a spiral like that, and I think they are related. Yeah, so I think there is a thing here where
it might be that models tend to represent features in similar ways between models, but the actual, in some sense, the actual algorithms that internally use those features can be different.
Yeah.
Depend more on the model architecture and the hyperparameters and whatever.
At the same time, no LLM has the same data unless you do perfect replications.
Yeah, that's true. But even if they don't
So-
have the same data exactly, like they have a lot of the same data. And they are the
Yeah.
general, like I don't know, you are going to find the same structure about numbers
Yeah.
everywhere.
Yeah. And also, like, because there's different RLHFs and different RLVRs and so on, which I assume to some degree, like, change the internal representations as well, and not to some,
Yeah,
like,
I mean,
slightly
the
change it.
reinforcement learning is also like talking about data seems harder on reinforcement learning.
Yeah,
right?
that's
Because the
true.
data is like
Yeah.
depends on the model, what the model outputs, and like there's no, it's not unsuper, like it's more for, it's not the same.
feel-
It's not the same kind of thing.
I feel like a lot of the innate dimensionality research, where like and like some of that LoRa fine tuning research, where it shows like the model weights are like really not changed. Like you don't change the model weights too much to change the different outputs, or like that you can use SAEs that were trained on the pre-trained version on the fine-tuned version. Like I think for a lot of the underlying representations, you're really not going to be changing too much. So it'd be more like what we were talking about before, that the algorithms for processing that like latent information might change, but the actual latent representation themselves probably don't change all that much, at least empirically.
Yeah, that makes sense. Although I wonder,
I think
how
they
much,
changed a little bit, yeah.
I wonder how much this is because the people don't train that much. Like they're just fine tuning a bit, and like how things are different. Like there is a lot of results saying that the reinforcement learning training, didn't change that much about representation, all that. But I feel like we don't really know if this is still the case on the setting of like the current, reasoning models, where maybe people do things like train the models on similar amounts of reinforcement learning I don't know if they actually got there yet, but like if you train the model with as much reinforcement learning training as pre-training or things like that, like when you're doing orders of magnitude more reinforcement learning, maybe that actually changes the model more than when it was a small amount of fine tuning over a pre-training model that was pre-training a lot more data. But like, I feel like we don't have a lot of evidence from this on the way, one way or another, because we don't have a lot of models that are trained with a lot of whatever reinforcement. Like this is a thing where the big labs have been more.
Yeah, I mean, at the same time, like
There is,
the
I guess, the
DeepSeek and Kimi
models,
models. Yeah, I'm surprised there is not Mech Interp there. I think it's because most people just cannot run it. So.
Oh, did you
I think
see?
that's why.
Did you guys see that Cohen released a whole bunch of SAEs?
I seen.
I didn't.
I think I linked it in the interesting findings. Maybe I did.
I
Maybe
should,
I
I
didn't.
should be checking the interesting findings channel more lately. I haven't been.
Oh, I
looking at-
didn't link it. Someone else did. QuantScope.
Oh, nice.
Yeah,
I
this is
feel like
interesting.
these days I spend too much time on Twitter, and the server spend more time on the server at the moment.
Yeah, I also spent too much time on it, but it's worth it sometimes.
Yeah, I mean, sometimes Twitter is also where you find things at the same time, unfortunately.
Yeah.
It's a shame that the publishing, like the posting about papers, the website is also the having the dumb arguments about the paper website.
Can you say again?
Yeah, I'm just saying that it's a shame that Twitter is both the people announcing papers and posting about interesting research and whatever website, and the dumb arguments website.
All right. Yeah. Well, I guess that comes from the scale.
I mean, I guess you can try to filter more, but
But hey, if you want, I found a very good way to filter blue sky to not give you slop. Well, give you much less slop. So
I think Blue Sky is better on a lot of ways on that. The problem with Blue Sky is that it has less scale and less people use it.
yeah. Like I found, like you can mute. There's a giant list of people that trash talk AI systems without understanding them. That you can just block them all in parallel, and then there's like extra feed that just upweights what you actually liked.
Oh yeah, the For You feed. Yeah, that's nice. Although
Yeah,
you can't get into a bubble on that. Like you
true.
only like things you agree with or whatever. But yeah, I think it's
Yeah, that's true.
definitely nicer than the Twitter feed that is trying to, or even the Blue Sky feed that is just trying to maximize you interacting with Twitter by making you angry.
Yeah, I mean, at least well, it's better to use less wrong maybe or something similar. So
maybe
but at least I write more of soft
I
text.
should probably spend more time reading less Brown and arguing with people on less Brown than arguing with people in that is more productive. In that I don't know, I had more interesting discussions with disagreeing with Stephen Prince than disagreeing with random people in Blue Sky. I should probably do that more. But yeah, anyway, going back to the paper.
Thanks, feel free to come later.
Oh yeah, thanks for
Quite a while.
yeah, and also feel free if you're interested in some paper, feel free to mention it.
Mm-hmm. Vision language symmetry grows as it increases. Hinting that they converge. Partially. Yeah.
Yeah.
Such end of feature this convergence. Law of large numbers. Apply to feature kernels. Deep learning networks can arise from implicit regularization or SGP.
Okay, yeah. So
I wonder if there is like some other like algorithm than as stochastic gradient descent that like completely breaks the Platonic representation hypothesis. Like,
but I guess the question is there some algorithm like that works? Or does the Platonic representation hypothesis is about the kind of algorithms that work?
I mean, if it's true that the brain doesn't use gradient descent, then maybe there is.
But maybe you'll find that it has similar representations too.
Mm-hmm.
Like for example, if there
are similarities
on the data and whatever, right?
Yeah.
You might find the thing.
That's true.
And you also, I guess, the different thing is, do JEPA models end up with similar representations?
Yeah, like I mean, you still use like in JEPA, you still use the transformers. The only thing you change is the learning objective. Like, well, if that's extreme oversimplification, but that's the primary one. Instead of predict the next token, you predict the.
I guess that I wonder how much that end up meaning actually JEPA models just end up learning the same kind of things, and it's not worth to take JEPA models because you just.
Yeah, this is one of the reasons why I don't understand Jan LeCun. He's like, it's gonna completely revolutionize and threshold lamps. Bro, like, you're only changing, quote unquote, only, it's still, there's a lot of nuance. Like, the objective, and
I mean, maybe
also
we could live in a world where it turns out that objective is better or something like just does much better, but maybe not, I don't know.
But it is maybe that I'm just dumb, and Jan LeCun is much more educated than me, so I don't know. I just don't see his conclusions follow from the JEPA papers I've looked at. Like, you still use transform, you still use gradient descent, and you calculate energies through instead of probability distribution, but like the difference, quote unquote, if I oversimplify it, it's like you don't normalize it.
If they are using transformers and gradient descent, where does you talk about latents and all that? How does that work?
You do contrastive loss. So at least okay, maybe LLM JPA is the best paper. LLM JPA. If you here's a in the paper there's a nice I think diagram. Is there a diagram? Okay, there is no diagram. There is a loss though. Let me find the loss. Oh yeah, there is a diagram. So here's the diagram.
Okay.
That's first thing, and second thing, I'm gonna take the. Oh, here's the loss. No, okay, here's the loss. Yeah, so you do normal LM stuff in this loss. So the first part is the cross entropy next token prediction, and the second is the JEPA thing. So, and in the diagram, you basically you wanna calculate the energy. So you have a text and you have a code, and you wanna make sure that the text is distinct than the code. So you encode the text, you encode the code, then you calculate cosine similarity in this case, and if it's like you want it to be lower cosine similarity for distinct things and higher cosine similarity for similar things. Yeah. So you add this into the loss. This is a hybrid kinda in this case. So so this is for LMs. In the causal JEPA, like because JEPA is a whole paradigm, so the architectures are very different. The causal JEPA, which is this one. Here they actually do the next latent prediction. Oh yeah, here it is. So in this diagram, you have you first collapse the video or the screen into these objects. So like it could be ball 1, ball 2 in a video or something, and then you predict the next time if the ball will change its position, for example. Yeah. So this one is the latent part. But in general, you can do more things with energy-based models. It's so general that it's hard to like say, oh, this is the specific JEPA thing, because it's like this is the specific next token prediction
right
thing.
now.
Say again.
Are you guys looking at the JEPA paper right now?
Yeah, I was trying to explain that. Cool.
Yeah, but by the way, I think I going to stop the recording because we kind of not.
Yeah, I think I'll read the.
Is JEPA the image model?
JEPA is a general way how to. Wait, let me just pull the original JEPA paper, the very original one, which